Welcome to Theory of Computation. This is lecture number 27. We have been discussing the Cook-Levin theorem, which, as I've told you, is one of the most important theorems in this course and one of the most important theorems in complexity theory. As you know, the Cook-Levin theorem says that one problem called satisfiability is NP-complete. That means all the problems in NP can be reduced in polynomial time to satisfiability. In some sense, satisfiability captures the whole complexity class NP. Well, what we want to do is understand reducibility, what reducibility is and what actually we mean by it. I want to illustrate the concept of reducibility through a very simple example today. Let us say that we can play two different games. One of the games is that I will think of a number and you can ask me any yes-no questions you want, and after asking me a certain number of questions, you will find out what the number is, and what you're trying to do is ask as few questions as possible. And you can ask any yes-no questions. For example, you can ask me if the number is prime or not, and I would say yes or no. You can ask me if the number is greater than 20 or not, and I would say yes or no. Let us think of another game. In the other game, I will think of an n-bit number, and now you can only ask me questions which are of the form, what is the first bit of this number, what is the second bit of this number, what is the third bit of this number, and so on and so forth. Well, that's the other game, in which your questions are much more restricted. You can only ask what is the ith bit of the number that I have thought of. Now, if you think about the first game, the questions in the first game are much more general, because any question that you're asking in the second game can also be asked in the first game. All you have to do is be a little clever. Remember, the first game allows you to ask any questions in which I will answer yes or no. Whereas in the second game, the only questions allowed are what is the ith bit. Now suppose if I want to find out what is the 17th bit of the number. Well, I can repose this question by saying, is the 17th bit of the number 0 or not? Well, then it becomes a yes-no question. So I can repose the questions of the second game into the first game. So in some sense, the language that is allowed for the first game is more powerful than the language that is allowed in the second game. On the other hand, I cannot necessarily translate all the questions of the first game into the second game. For example, if I want to find out if the number is prime or not, as we know, a single bit doesn't have that information. So it would be impossible for me to rephrase that question in the second game. And that's what the essence of reducibility is. In reducibility, what we have is two languages. So for example, we had the language of satisfiability. What that means is I can give you any Boolean formula and ask you whether it is satisfiable or not. And you will answer yes or no according to whether the formula is satisfiable or not. That's the first language, satisfiability. The other language that we looked at last time, we called it three-color. In this game, I cannot present to you a formula. What I can present to you is a graph. I give you a graph and I can ask you whether the graph is three-colorable or not. And what you can do is you will say yes if the graph is three-colorable, and you'd say no if the graph is not three-colorable. Last time we proved that three-color was reducible to SAT. What does that mean? That means the first game is much more general than the second game. Any question in the second game can be reposed as a satisfiability question. So if I have a graph, from that graph, I can quickly compute a formula and hand you that formula, Boolean formula, and ask you if the formula is satisfiable or not. And if you say yes, the formula is satisfiable, then I would know that my original graph was three-colorable. And if you say no, the formula is not satisfiable, then I would know that my original graph is not three-colorable. So last time the theorem that we proved, which said that three-color is reducible to satisfiability, essentially says that the language of satisfiability is more general, or at least as general as the language of three-colorability. You can repose all three-colorability problems on finite graphs into satisfiability questions. Furthermore, reposing these problems does not take too much time. It takes polynomial time. And that is a very important point, because what you don't, since we are studying complexity theory, we really do care how much time it takes for us to change a question into another kind. Now, since we said that we can repose the problem in polynomial time, now if somebody were to magically discover a polynomial time algorithm for satisfiability, or if somebody were to make a machine or some aliens were to answer satisfiability questions for us, then we'd be very happy, because if we ever want to know if a graph is three-colorable, we can quickly repose the problem as satisfiability question and ask the aliens, who will give us the answer in polynomial time. So this means if somebody is looking for a polynomial time algorithm for satisfiability, they're doing a little more. What they're doing is looking for an algorithm for satisfiability, which is polynomial time, and that algorithm will immediately give us a polynomial time algorithm for the three-color problem. Now, the Cook-Levin theorem is much, much more general than what we have proved. As you know, three-colorability is in NP. We saw a very easy verification algorithm for three-colorability. Well, how would we verify if a graph is three-colorable? We'll ask for the graph and a three-coloring of it. And then we'll check if the three-coloring is proper, if every vertex is colored with exactly one color. And then we'll go through every edge and make sure that the two endpoints of every edge are colored with different colors. So that shows that three-colorability is in NP. So we have one language in NP, and we showed that that is reducible to satisfiability. The Cook-Levin theorem says that there is nothing special about three-color. The only thing about three-color is that it's in NP, and this theorem holds for all languages in NP. So let us look at the Cook-Levin theorem. Let us once again recall that satisfiability is the set of all formulas phi which are satisfiable. And we also saw that satisfiability is in NP. We gave an easy verification algorithm for it. The algorithm takes a formula phi and assignment tau and checks if tau satisfies phi. So we saw that satisfiability is in NP. Now the Cook-Levin theorem asserts that satisfiability is NP complete. If you recall the definition of NP complete, there were two requirements. First of all, the language must itself be in NP, and we have already shown that for satisfiability, so we are done with that part of the proof. The second requirement is that everything in NP should be reducible to that language. So if you're saying satisfiability is NP complete, then everything in NP should be polynomial time reducible to satisfiability, and that is the heart of the Cook-Levin theorem. Once we establish that satisfiability is NP complete, that would be an extremely important result. One of the consequences of that result would be, of course, the following theorem of Cook and Levin, which says that P is equal to NP if and only if satisfiability is in P. So, to separate the class P and NP, all we have to do is find out if satisfiability is in P or not. So, whether P is equal to NP, that question is equivalent to the question of whether there is a polynomial time algorithm for satisfiability or not. So, the whole class NP, in some sense, is represented by this one concrete problem, satisfiability. Now, last time we proved a very special case of the Cook-Levin theorem. We showed that three-color is polynomial time reducible to SAT. Well, if we've already proved the Cook-Levin theorem to see this particular instance of Cook-Levin theorem, all we'll have to do is observe that 3-color is an NP, and since every language in NP is polynomial time reducible to SAT, therefore 3-color is also polynomial time reducible to SAT. Why did we go through all this trouble of reducing 3-color to SAT, and now we are going to prove this much more general theorem which says everything in NP is reducible to SAT? The reason is because I wanted you to get a feeling for what satisfiability is, how powerful that language is, and what kind of things we can express in it. Remember, what we did in that proof was we said if we have a graph, we would look at the graph and then we'll come up with a formula phi, and this formula will express the following things. It will express the fact that each vertex is colored with exactly one of the colors red, blue or green. And then we said we will make another formula that expresses the fact that every edge, the endpoints of every edge are colored differently. If we can make these two formulas, then if we take the AND of these two formulas, that would say that every vertex gets a distinct color from red, blue and green, and every edge, the two endpoints of that edge are of different colors, and that would express the fact that the graph is 3-colorable. Now this formula phi, since it expresses this fact, which means it will be satisfiable if and only if we can satisfy these requirements, therefore this formula will be satisfiable if and only if the graph is 3-colorable. So the language of satisfiability is extremely powerful. Our goal is now to prove the Cook-Levin theorem in its complete general form. What do we have to show? Let's think about what we have to show. We want to show that if a language L is an NP, then L is polynomial time reducible to SAT. Let us start with some language L that is an NP. What do we know about this language? Well, if you think about it, we don't know much about this language. All we know is that this language is an NP. On the other hand, if you look at our previous proof, when we were dealing with 3-color, we knew a lot about the language. We actually knew the definition of the language. We knew the language had to do with graphs, and it is the set of all encodings of graphs which are 3-colorable. So we knew that the problem came from graph theory. We could use our expertise in graph theory to come up with the reducibility. However, now we have a language which is an NP, and all we know is that this language belongs to the class NP. So we do not know whether this is a problem from graph theory or logic or some other kind of subject. All we know is that this language belongs to NP. Well, now what we will do is we'll spell out what does it mean for a language to belong to NP. So let's spell that out. The only thing we know about L is that it is accepted by a non-deterministic Turing machine M in non-deterministic polynomial time. So let us record these facts. Let M be a non-deterministic Turing machine that accepts L in time n to the k. So since L is an NP, there must be a non-deterministic Turing machine which accepts L in non-deterministic polynomial time. So we fix a machine M that accepts L in non-deterministic polynomial time, and we let n to the k be the upper bound on the running time of this non-deterministic Turing machine. That is exactly what it means for a language to be in NP. It means it's accepted by a non-deterministic Turing machine in time n to the k for some fixed constant k. Now, what do we want to do? Well, what we want to do is we will change this problem. We will look at x, and what we want to do is we want to come up with a formula phi sub x. And this formula phi sub x will have the property that it is satisfiable if and only if the non-deterministic Turing machine M accepts x. Well, so this formula phi sub x must be computable in polynomial time from x. That would show us that this reduction is a polynomial time reduction. So let's start and see what our goal is. What we want to do is come up with a reduction. This reduction will take an instance x and convert it into a formula phi sub x, such that x is in L if and only if phi sub x is satisfiable. Now, what we will do is, we will let this formula phi sub x express something. It would express the fact that the non-deterministic Turing machine M accepts x. Remember, in our last reduction, we came up with a formula phi, which was expressing the fact that a graph G is 3-colorable. Now we will have a formula phi sub x, which would say something about the non-deterministic Turing machine. So we will look at this non-deterministic Turing machine and the input x, and then construct our formula phi sub x in such a way that it will express the fact that M accepts x. By expressing, I mean that phi sub x is going to be satisfiable if and only if M accepts x. Let's see how to do this. Note that if x is in L, then there is at least one computation branch of the non-deterministic Turing machine M that accepts x. Remember, when you have a non-deterministic Turing machine and you give it one input, then its computation is modeled by a tree. And this non-deterministic Turing machine is said to accept an input x if and only if at least one branch of this non-deterministic Turing machine accepts. What that means is, when we give this machine an input x, the machine has several choices at every step. And there is at least one sequence of choices that leads it to a final state, that leads it to accepting this input x. Now what we can do is, we can take that particular computation, which is an accepting computation of M on x, and write it in a table. So let us write this computation in a table. The first row of this table will consist of the initial configuration of the machine on the input x. The second row of this table will consist of the configuration after one step, and so on. How would this table look like? Let's have a look at this table. This table is going to be a square, with the first row being the first initial configuration of M on x, and the second row being the second configuration of M on x, and so on, and the last row is going to be an accepting configurations. Let us make some observations about this table. So you saw a schematic diagram of this table. All you have done is written down one accepting configuration of M on x, written it down in a table. The first row is the first configuration, the second row is the second configuration, and so on and so forth. Now, if you present this table to somebody, they would be able to verify that at least one branch of M accepts x. All they'll have to do is look at the first row and check whether it is the initial configuration of M on x. Then they'll look at the second row and they will consult the transition function of the Turing machine M and make sure that the first configuration yields the second configuration, that we are not cheating anywhere. And then they will make sure whether the second configuration yields the third configuration, and so on and so forth. Once they've made sure that each configuration is yielded by the previous one, they will just check if eventually the machine reaches a final state. Once they've performed all these checks, they would know that M accepts x, and that would be a proof that x is in L. What we want to do is, we want to express all these things, all these checkings that we think a human being can do, into a formula phi, and this formula phi will be satisfiable if and only if all these checks go through. Now let's think a little bit about this table. Let's think about it a bit, how it would be, how big it would be, and make some observations. First of all, this table will have at most n to the k rows, since the machine accepts in time n to the k. So we know how long this table is, how many rows this table has. We do not need to have more than n to the k rows, because the Turing machine accepts in time n to the k. So there's at least one accepting branch of M which takes only n to the k steps. So the table needs to have at most n to the k rows. The second thing to observe is that this Turing machine will only scan n to the k tape symbols. So we only need to keep n to the k columns in this table. Since this Turing machine runs in time n to the k, it can never use more than n to the k tape cells. Hence, after n to the k tape cells, we'll always have blanks on our tape. Therefore, if we just keep n to the k cells for each configuration, we will have all the information needed for that configuration. The rest of the symbols on the tape will be blanks. So this table will be of size n to the k by n to the k. And that is a total of n to the 2k cells. N to the 2k cells, when k is a constant, is polynomial size. So far at least we have one good sign. The table that we want to build has polynomial size. Now what we want to do is we want to look at how this table will actually look like and how we can express those properties of this table into the language of satisfiability. Remember, our goal is to reduce this language to satisfiability. So this table will have n to the k times n to the k cells. And this table is a proof of the fact that M accepts X. Thus, it is a proof of the fact that X is in L. Let us look at a schematic diagram of this table. As you can see, this table has n to the k rows and n to the k columns. Each row is one configuration. The first row is the initial configuration. The second row is the configuration that follows the initial configuration, and so on and so forth. And then it has n to the k columns. For convenience, we have put hash signs at the end of each configuration and at the beginning of each configuration. So this table will look like, if anyone has this table, they can confirm that X is in L by checking the following three things. First of all, they would check if the first configuration is an initial configuration. Second of all, they would check if the last configuration is an accepting configuration. And lastly, they would check if the ith configuration yields the ith plus first configuration. That is, that we have not cheated, we have used the transition function of this Turing machine M properly. So if somebody performs these three checks, they would know that M accepts X and they would be convinced that X is in L. Now we will relate all this to satisfiability. Let X be a string in L. Well, X is in L if and only if we can make a table that satisfies the above properties. But now we do not want to think about this table. What we now want to think about is an instance of satisfiability. So now we want to think about propositional formulas. We want to think about Boolean formulas that are made out of Boolean variables which take values true and false. And we want to make these formulas true or satisfiable if and only if we can make a table with certain property. Well, let us first look at the contents of this table. What can appear in one particular cell in this table? Let's think about it. In a configuration, a cell in this table will have a symbol from the set C, which is equal to Q union gamma union the hash symbol. So if you look at any one cell of this table, it will either have a work symbol of the Turing machine, or it will have a state, or we have added the hash symbol. So each symbol in a particular cell in this table will either be a state or a work symbol or the hash sign, and we combinedly call this set C. So each cell will have one symbol from the set C. Now what we want to do is we want to say that make a table and fill each cell with exactly one symbol from C. Can we do this in the language of satisfiability? So let's look at one particular cell. Let us say cell number ij. Can we make a formula that expresses the fact that each cell has one symbol from C in it? The table is made out of many cells. Let cell ij denote the ijth cell in the table. What we will do is we will make variables x, I, j, s for each cell and each s in C. If the cell ij contains s, then we will set the variable x, I, j, s equal to true. Otherwise, we will set it equal to false. So, for example, let us say that the ijth cell contains a. Then we'll set the variable x sub I, j, comma a to be equal to true. On the other hand, the cell x sub I, comma j, comma b will be set to false because the ijth cell does not contain b. Now what we will do is we will use a trick to come up with a formula which will be satisfiable, and the satisfying assignment will give us a tableau in which each cell contains exactly one symbol from the set C. Let us look at one cell and this formula first. So let us look at this following formula which appears on your screen. It seems like a very horrendous, very large formula, but what we can do is understand it one by one. So let me tell you first what is this formula saying. If you want to satisfy this Boolean formula, that would mean you will have to put exactly one symbol in the cell ij. Your satisfying assignment will actually correspond to putting exactly one symbol from the set C into the cell ij. Let's see how this formula is expressing this fact. Let's review why this is the case. Let's look at the first part of this formula, and if you see that's a OR, it's a OR over all S in C, and it's a OR of xi, j, comma s. So the first part of the formula is saying that either you have to set xi, comma j, comma s1 equals true or s2 equals true, or so out of all these s's, one of these variables must be true in order to make the first part of this formula true. So what is being said is I have ORed over all the s's in the set C over the Boolean variables x, I, j, s. The only way to satisfy this formula is to at least satisfy one of the variables, at least set one of these variables to true. So this means the first part is saying you must put at least one symbol in the cell ij. Of course, if you said xij a equals to true, that means in the cell ij you're putting a. If you said xij b equals to true, that means in the cell ij you're putting b. If you said xij q1 equal to true, that means in the cell ij you're putting q1. On the other hand, if you said xij c equal to false, that means in the cell ij you're not putting c. Now, to satisfy the first part, it says in the cell ij you must put at least one symbol from C. Okay? However, this part of the formula will be satisfied even if you were to put A in the ijth cell and B in the ijth cell. So it'll be, the first part would be satisfiable even if there are more than one symbols put in the cell, which is what we don't want. And that's why we have ANDed this with the second part in this formula. Let us have a close look at this second part of this Boolean formula and let's see what it is saying. Well, let's first look at the inside of this. So let's for a moment fix a symbol S from C and a symbol T from C. So what we're doing is we're looking at two symbols. We're fixing two symbols S and T from the set C. Remember that S can go in a particular cell and T can go in a particular cell, and we're concentrating on the cell ij. Now if you look at inside, it says xijs, the negation of that, or xijt, the negation of that. Let's try to read this in English. Xijs means is true when the ijth cell contains S. So it will be false if the ijth cell does not contain S. So this thing is saying either the ijth cell does not contain S or the ijth cell does not contain T. What this means is whenever you take two symbols S and T, either S is missing from the ijth cell or T is missing from the ijth cell. So this says that in the ijth cell, you cannot simultaneously put S and T. You must not put at least one of them. Now, what we're doing is we're ANDing this with over all pairs, S and T, such that S is not equal to T. So what we're saying is there cannot be any pair of symbols which is both present in the cell ij. That's what the second part is saying. The second part is saying is that if you take any pair of symbols, let's say you take the pair AB, or you take the pair PQ, or you take the pair Q1A, both of those symbols cannot be present simultaneously in the cell ij. So the first part is saying that at least one symbol must be present in the cell ij, and the second part is saying is that no two symbols can be simultaneously present in the cell ij. Well, it takes a little while to figure out that this whole formula is saying that exactly one symbol must be present in the cell ij. So this formula is satisfiable if and only the way you can satisfy this formula is by assigning the variables in such a way so that that corresponds to putting exactly one symbol in every cell ij. So if I want to satisfy this formula, then what I need to do is just put exactly one symbol in the cell ij. Once we have this, we can AND this over all the cells and say that we have a proper tableau. Let's see how we'll do that. Let us look at this formula, which is even more horrendous than the previous one. However, if you look at it, it's not that bad. Whatever is inside the square brackets you've already seen before. What's inside the square brackets is saying, well, put exactly one symbol in the cell ij. So all we have to understand is what is outside the square brackets. Outside the square brackets, we're saying we'll AND this over all the cells ij. What we're saying is every single cell of this tableau must have exactly one symbol from the set C in it. So this formula, which we are now calling phi sub cell, is satisfiable only by assignments which correspond to putting exactly one symbol from the set C into the tableau. So if we want to satisfy phi sub cell, well, that would mean somehow that corresponds to making an n to the k by n to the k tableau, and in each cell putting exactly one symbol. This is our formula phi sub cell, and you can think of it as just saying, well, make an n to the k by n to the k tableau, and it doesn't really check anything else about this tableau. It only checks whether you've made this tableau properly, whether every cell has exactly one symbol in it. Now what we will do is add more formulas like this, which will start checking various properties of this tableau. Now let's say we have an input x1, x2 up to xn. What we want to say is that the first row of the tableau corresponds to the initial configuration. Remember, what we want to do is we want to say several things about the tableau. What we want to do is we want to say that X is accepted by the Turing machine M, which means that there is a tableau. The second property of the tableau is the first row corresponds to the initial configuration. The third property is that the last row corresponds to the final configuration. And the fourth property is that each successive row is gotten from the previous one through the yields relationship of the non-deterministic Turing machine. So phi sub cell only expresses the fact that we have a tableau in which each cell has a particular symbol from the set C. Now what we want to do is we want to come up with a formula which will say that the first row is the initial configuration of the Turing machine M on input X. So let's take an input X, which is X1, up X2, X3, all the way up to Xn. What we will do is consider this formula which we call phi start. Let's see what phi start says. Phi start says is the formula x11 hash and x12 q0 and x13 x1 and x14 x2 all the way up to x1 n plus 2 xn. Well, what does it mean when I say x1 comma 1 comma hash? How can I satisfy this formula if x1 comma 1 comma hash is ANDed with the rest of whatever comes in this formula? The only way to satisfy this formula is to make x1 comma 1 comma hash equal to true. To make x1 comma 1 comma hash equal to true means it corresponds to putting the hash symbol in the corner left of this tableau. This means I have to put the hash symbol in the corner left of the tableau. So this says that the first symbol of the first configuration must be a hash sign. What does it mean? Then I have ANDed that with x1 comma 2 comma q0. That means the second thing that comes in this configuration is the state q0. After that I have written x1 comma 3 comma x1. This means that the third symbol in this tableau must be x1. Similarly, it says that the fourth symbol in this tableau must be x2 and the fifth symbol must be x3 and the sixth symbol must be x4 and so on, all the way up to n plus second symbol, which must be xn. Now let's read this formula after that. What does it say? It says, so the first thing says that the first symbol must be a hash sign followed by q0, followed by x1, followed by x2, all the way up to followed by xn. And then the remaining part says that all the remaining symbols must be blanks and the last symbol must be a hash sign. That's precisely saying that the first row is the initial configuration. So if you want to satisfy phi sub start, what you have to do is in this tableau put in the first row the initial configuration. And remember what the initial configuration of the Turing machine M on the input X is? Well, what we do is write down q0 followed by the input, followed by all blanks. And that's what is being insisted by phi start, is that the first row of this tableau must be the initial configuration of this Turing machine. So this formula says that the first row of the tableau is the initial configuration of the Turing machine M on the input X equals x1 up to xn. So what we have been able to do is use the language of satisfiability to express a few things. Firstly, we have expressed that we must fill out this tableau by putting exactly one symbol in each cell. That was phi sub cell. The second thing that we have done is made this small formula, this very easy formula, which will be made true if and only if we were to fill the starting configuration as the first row in this tableau. We're not done yet. We have a lot more work to do. What we want to do is we want to express the fact that M accepts X, or in other words, this tableau has at least a accepting state somewhere. Can we come up with a formula which captures that? Well, let's look at that. That's not very hard. Let's look at this formula, and as you can see by now, you should be able to look at these formulas and not get scared. I call this formula phi sub accept, and it is the OR over all the cells. So we are ORing over all ij of the variables xi, j, q accept. Remember, when xi, j, q accept is true, that means in the ith, jth cell, there is the state q accept. So since here we are ORing over all the cells, what this formula is saying, somewhere in this tableau, I must see the accepting state. So this formula phi sub accept is going to be true if and only if in the tableau you have put the state q sub accept somewhere, or at least somewhere an accepting configuration of M has appeared. So this formula phi sub accept captures the fact that this tableau is encoding an accepting configuration. Phi sub start is simply saying somewhere in this tableau I must see the state q accept. And that's the same as a person looking at the tableau and you're trying to convince the person that this tableau corresponds to an accepting computation of M on X. Well, the person says, well, show me q accept somewhere in this tableau, show me where the machine has accepted. And we do that using Boolean logic by saying, well, somewhere in the tableau q sub accept must appear, which means xi comma j q accept must be true for at least one ij. So we OR all of those variables to create this formula. Lastly, what we want to do is create the most important formula that we are going to call phi sub move. This formula will say that each row comes from the previous row of the table through a legal move of the Turing machine. Remember, so far whatever we have been able to express through these formulas phi sub cell, phi sub accept and phi sub start doesn't have much to do with the Turing machine itself. All we did was we said that the tableau must be filled properly. The first row must be an initial configuration. We must see the accept state somewhere in the tableau. But now what we want to say is that this tableau actually came from a computation of the Turing machine M. This means that the first configuration yielded the second configuration, and the second configuration yielded the third configuration, and the third configuration yielded the fourth one, and so on and so forth. Well, if all of that is true, then we will be convinced that M accepts the input X. Now, how are we going to come up with a formula phi sub move which will ensure that the first configuration yielded the second one, and so on and so forth? Well, for that we need one more concept, and that concept is going to be of what we call legal windows. Let's look at this concept. Let us consider a window of size 2 by 3 in the tableau. So imagine this huge table you have, and what we want to look at is 2 rows and 3 columns. So only a window of size 2 by 3. So what we want to do is we want to zoom in onto this tableau and just look at a small piece of it, and a 2 by 3 thing is what we would call a window. So we would only look at a 2 by 3 window. A window will be called legal if it does not violate the action specified by M's transition function. Well, what does it mean that it does not violate the action specified by M's transition function? What it means is that if we look at this window, we should be able to convince ourselves that if the Turing machine M were to operate, it would yield this part of the configuration, can possibly yield that part of the configuration. We will actually define what exactly a legal window is. But before that, what I want to do is I want to explore this notion a bit intuitively and informally before going to the formal definition. In fact, one of your exercises would be to write down the precise definition of what a legal window is. However, right now we would try to understand this concept through examples and intuitively. So let's look at an example of what legal windows are. For that, what we need to do is go back to a concrete non-deterministic Turing machine. So let's take, for example, the following non-deterministic Turing machine. Suppose we have a Turing machine M which has the following moves. When it's in the state Q1 and it reads A, it moves into the state Q1, so it stays in the same state, writes a B and moves to the right. If it's in the state Q1 and reads a B, it can either go to the state Q2, write a C and move left, or go to the state Q2, write a A and move right. Now, let's look at some examples of a legal window. So, remember what a legal window is going to be. If you think about a non-deterministic Turing machine or a computation of a Turing machine, there's the tape and the head is moving on the tape and changing the tape. What we want to do is look at 3 cells of the tape at a given time. We want to focus on 3 cells and see what will happen after one step. And a legal window is going to be 3 cells followed by the 3 cells, and what we want to do is be able to make sure that these 3 cells will change the way the machine specifies it. If it is not possible, we'll call those windows illegal. Let's look at one example. This is an example of a legal window. You have the symbol A followed by Q1 followed by B. This means that the Turing machine is in the state Q1 and is reading B, and before B the symbol A is on the left of the head, but the symbol currently being scanned is B. Since delta of Q1 comma B is C and move left and go into the state Q2, therefore if it is possible for this Turing machine, then go into the configuration in which instead of A we read a Q2, that's because the head has moved to the left. Instead of the B or Q1 we read a A, and instead of the B we read a C. The machine replaced the B with a C and moved to the left. So this is a legal window. So this is something that we can possibly see happening if this Turing machine were to operate. So we call this a legal window. Let's look at another legal window. Once again, the top is the same, but now you'd see that the A symbol has been not changed from A to A. Q1 has been changed to A and B has been changed to Q2. Well, the machine was in the state Q1 and it was reading a B, and it took the second choice. So it replaced B with an A and moved to the right. So in the new configuration, if we look at what will come in the tableau underneath, we'll see an AAQ2. So this is an example of another legal window. Let's look at another example of a legal window. This is a legal window which is AAQ1, AAB. The only information we have is that the machine is in Q1. When we look at this legal window, we're not reading anything on the right of the last thing in the window. We know that the machine is in state Q1, but we don't know what it's reading. Well, in this case from Q1, it's possible for the machine to move to the right. And whatever it replaced will be the next symbol which will come there. Therefore, we will call this a legal window. Let's look at the next legal window, which is ABA and ABA. Well, why is this a legal window? Suppose you have A followed by B followed by A written on the tape, and the tape head is very far from this section of the tape. So the tape head is far away. Then in one step, the tape head cannot change any of these symbols. So it is possible to go from ABA and have no change occurring. Therefore, ABA and ABA is once again a legal window. Let us look at a couple of other examples. In this window, on the top we have ABA, and on the bottom row we have ABQ2. This window is legal because the tape head may have been to the left of A, it may have been to the right of A, and it may have moved left, and therefore we will call this a legal window. Let's look at the last legal window that we have, which is BBB on the top row and CBB. The tape head may have been scanning this B, and we don't see it because it would have been to the left of the B, and it may have changed this B to a C. Therefore, once again, this is a legal window. Well, we've been looking at examples of legal windows, and you've seen several legal windows. Now let's look at a few examples of windows which are not legal in order to see the difference between what is a legal window and what is not a legal window. So let's look at the next example, and this window is not legal, mind that. In this window we have ABA in the top row, and then we have AAA. This window cannot possibly be legal because a Turing machine only changes symbols which are under its tape head. If we have AAA, that means the middle A is not being scanned by the head, and therefore it cannot be changed. Therefore, this window is illegal, or it is not legal. Let's look at the next example. At the top we have AQ1B, and in the bottom we have Q1AA. Well, if we examine the transition function of our Turing machine M, the Turing machine that I told you earlier, this move is not allowed by the M's transition function. Therefore, it is not a legal window. So anything that cannot happen, that we cannot actually see when a computation of M happens, is called an illegal window. Anything that we can see that happens would be called a legal window. Now our plan is going to be this. What we will do is we will try to express the fact that every window in our tableau is legal using the language of satisfiability. After that, we will actually prove that if every window in a tableau is legal, that means that the tableau actually corresponds to a computation of this Turing machine. Once we've been able to do that, we'll finish the proof of the Cook-Levin theorem. We'll have to wait for the next lecture for us to finish this proof. I thank you for your time. Thank you and goodbye.